So that was the first mistake, right? I wrote y equals 0 and it's supposed to be x equals 0. So x equals 0 is the boundary in the back there. Z equals 0 is the bottom. I've got x plus 2y equals 4. So let's see, that means that we have a 4 and a 2 here. And we have z equals y squared. So that's coming along like this and this. Okay. So here's one of those cases. I wrote y equals 0, but I didn't really need y equals 0 because I was going to get y equals 0 anyway because of that other surface. So at this time, because it's a volume problem, you have to watch out. Maybe the surface is going to supply part of the boundary. Anyway, so that's still the right picture, or it is the right picture. And so I want to do the integral of, let's see, it's y squared in here. And I said I recommended dy dx. So x runs from 0 to 4. Is that where I messed up? Yeah. That's where I messed up. Okay, and the rest of it, I hope, is right. Okay? Then do I need to calculate it out?
No, I think the other one is also wrong.
The other one? What other one?
0 to 4, 0 to 4 minus 2x. I don't know.
Okay,
I think I got a negative half x plus 2.
Okay. So, or did I write down?
Yeah, you wrote down the equation is
x plus 2y is 4.
Mm-hmm.
And then I have to solve it for y.
Yeah.
And I have to get 4 minus. Okay.
And I calculated it, and I got, I got 16 over 3.
That sounds good enough. I'm not going to argue with it. Oh, and 16 over 3, that would be 5 and a third. And here I have 10 and 2/3, which would be twice as much. Yeah, I think 5 and a third looks like a better choice since the thing is scooped out. So, all right. So anyway, you're which one, 9 or 10? Did you want?
9.
Okay.
10 I have a problem.
Okay, find the volume of the solid cut off from the first quadrant by the parabolic cylinder whose equation is. And when I was doing the answers, I just didn't even see that when I went from 8 to 10, and then I noticed that later, and I said, it's too late, and I'm supposed to be grading other papers. All right, so anyway, z equals 4 minus x plus y squared.
I think the real problem I had with this one was like what it looked like.
Okay, well, so if you did 4 minus y squared, that would be like this, right? 4 minus x squared would be like this. 4 minus x plus y squared is on a 45-degree line like that. That makes sense? Okay. So, my I really should have had put the picture on the computer drawing of the picture. Anyway, so again, it's not this way. It's kind of like a tunnel, but not a tunnel along the x-axis and not a tunnel along the y-axis, but halfway in between. So it says the center stripe on the road through the tunnel is right there. That's y equals negative x. This is positive x, positive y. And so the top of the tunnel is over this line, and this thing is coming here, and it cuts through on the line x plus y equals 2. Why is it 2? Well, because that's what would give me 0 here.
And then the other one, we only care about the 2, because in the first option,
Yeah. So this is it. These two curves are at right angles here. So if I were to give you find the angle between these two curves at this intersection point, it would be 90 degrees. And basically, these are horizontal here. So you're integrating over a triangle. And we get the integral from 0 to 2, and take your pick, it doesn't matter. Dy dx, y naught. 4 minus x plus y squared. Dy dx. And then, so we'll draw the triangle and solve it for y. Y equals 2 minus x. We're going 0 to 2 minus x. And that's the setup. Now, I'm kind of wondering, is this one worth pushing through any further? I think there's something neat that comes along here. I just made up this problem, or this might be the one I stole from another book, but I modified it a little bit just because I like. No, I think it's the other one that I stole and modified. Anyway, so I get 4y minus 1/3 of x plus y cubed, right? I could multiply this out and say x squared plus 2xy plus y squared, and change all the signs. And so then I'd have 4 different integrations to do. This way I've only got 2 integrations to do for that thing. And notice what happens when I plug these limits in here. So I'm going to have the integral 0 to 2 of 4 times 2 minus x. And what happens on this end, I've got 1/3 of x plus 2 minus x cubed, right? When I plug this in, that's the y right there. So that's just going to give me a negative 1/3 of 8. And then I'm going to get a positive because I've got to subtract for the lower limit, but I've already got a minus. Well, that's just going to be 1/3 of x cubed. Oh, look, difference of cubes. Anyway, I don't really see much else that could happen in this one, so I think I'll just say it's 7 at this point. But again, just for 2 reasons, it's better to keep this thing together. Reason 1, I've got fewer terms. And reason 2, when I put this into this thing, it just falls apart. Okay, any other questions?
I have a lot, actually.
Yeah, what?
If anybody else has any questions, though, I don't want to follow questions.
Oh, no. All right, no other questions from you for the moment. Anybody else? All right, what else you got?
I think number 11 is Centennial.
11, same set? Tell me about it. You're hitting all these new volume problems that I haven't had a chance to digest over here. I mean, I just was
Yeah, they're
thinking we needed some more volume problems. All right, so we have first octant, and I need to restate some of these others. I think this one's okay though. First octant bounded by the XY plane, the YZ plane. So let's see, here is the XY plane.
What problem is this?
Number 11.
On the same supplement?
On the same supplement. The YZ plane, so well, that's the plane of the board anyway. And the plane x equals 2y. So if x equals 2y, that come out like this. And the cylinder, y squared plus z squared equals 9. So anyway, okay, so this line is parallel to the x-axis. The z-axis, the bottom part of the z-axis doesn't have anything to do. This thing comes down here. Okay? So we have this cylinder, and it's like I treat it like a, what kind of cake is that is popular at Christmas time, where it's just like a roll or something, and then you can slice it this way and get bigger like that, especially if you slice it that way. So anyway, that's what I want to get at. So now my region is a triangle. It's a triangle that's next to the y-axis. So it looks like this. That's my base. And the thing I'm integrating, this was y squared plus z squared, was it 9? Yeah, okay. Y squared plus z squared is 9, so I've got z equals the square root of 9 minus y squared. And then we have to do our area form. And T for triangle, or B for base, or whatever. And I have to decide dy dx or dx dy. And if I set up dx dy, dy dx, that means I'm going to get arc sines and all that stuff. So I think it'd be better to do dx dy here. After a few examples, most people, I think, get prejudiced in favor of dy dx. So I like to give some where it's better to do dx dy. Y runs from, let's see, y runs from B. So what plane was this? Did we have? X equals 2y. All right. So my line, well, x equals 2y. Well, that's nice because I don't need any fractions then. So I get x.
Can I ask a quick question?
Yeah.
Well, how did you know that?
Apparently, no, you can't because you asked these questions and we've been working on them a lot.
How did you know that the triangle was on top rather than like on the bottom?
Well, because if I had done this part of it, it would have gone to infinity. Oh, and besides that, and not that they can't go to infinity, but in this case, the volume would have been infinite. You know, with improper intervals, sometimes you can go to infinity and still get a finite answer, but it wouldn't be in this case. The other thing was, it said that the line x equals 0, the plane x equals 0 was part of the boundary. So that's behind this thing. So yeah, that's how I knew. And so once I knew that that was it, I knew that this was hugging the y-axis. So I drew it up there. So anyway, this is 0 to 2y and 0 to 4, no, to 2. To 3. because, again, the three-dimensional object is supplying part of the boundary in 2 dimensions. So, because of this 9 right here, we're going to get y equals 3. See, this is the intersection with z equals 0 and this crap. So anyway, we do one integral. Oh, and look how nice I was to you. By putting it at 2i, that means that I've even got the complete differential here. Right? So when I let 9 minus y squared equal u, okay, I don't have the minus in there yet. But anyway, du is minus 2y, and etc. I haven't heard of that. Anybody know that? Sharon? Which desk? Oh, good, because that one I'll see is. Okay. Well, where was I?
You were on 7.
I was on at 7. Okay. Well, we'll leave it at 7. That one here is 2. What else you got? Oh, I've got the answers right here.
Yeah,
Except I didn't have
those are mine. I printed that out.
So the balance will change from 0 to 3 to from 9 to 0, right?
Oh, yes, yes.
With new substitution.
When I go to the substitution.
Okay.
Anything else?
No.
I don't have the examples with me because I don't really print out the supplements. I just leave it online.
I see.
I have a couple of questions. I just can't remember the problems.
All right.
Okay.
This will be bright enough for me to see it.
You said supplement 8 is going to be on?
Yep. We better do some of that, huh?
Yeah, that's probably good.
All right. Well, while he's looking through, we'll look at supplement 8. I should do one of these improper integrals. For example, well, let's at least set up problem 1. Oh, but 1 is already set up for us because I gave you the limits. So really, this is just a straight calculus 2 type exercise in part A. And I don't think I'll bother with it, but it does say draw the reach of integration. So what's the reach of integration? What kind of figure? I think it's not quite as important to be able to look at the limits and draw the picture, but it's almost as important as being able to look at the picture and draw the limits. So you just write down 4 equations here. X equals 1, x equals 0, y equals 1, and y equals infinity, or maybe we can say y goes to infinity or whatever. So x equals 0, right there.
Is it going to be like a rectangle that keeps going?
Just get a rectangle that keeps going, that's precisely right. So here is my x equals 1, here's my x equals 0. Y equals 1 is right here. And then y goes to infinity, so it's above. I could just as well.
I wanted to say that, but I wasn't too sure.
Ah, the strength of your conviction. So there it is. And somebody asked last time if infinity counts as a constant, and the answer is yes, it counts as a constant.
So you can
Switch around. Is that what you're saying?
or you
Well, I was gonna say, that if I wanted to see in problem 2 for a minor challenge, recalculate it in the reverse order. And I thought you were gonna say, so you can just switch these around if you want to. And whenever they're all constant, yes, you can. Anyway, if you do switch them around, what I'm saying here is that the problem is a little bit harder. And that's kind of surprising because the limits are all constant. But anyway, it can make a difference which direction you go. All right, but I don't really want to push that anymore. I want to talk about, setting these things up. So how about problem 3? So I want an integral in the first quadrant. So this is going to be an integral over Q1 of dA over x plus y plus 3q. And the x and y enter in here symmetrically. And so it really doesn't matter whether it's dx dy or dy dx. If it really doesn't matter, a lot of times I'll choose dy dx simply because that means I have an x left over at the end instead of a y, and we're more used to doing x intervals. So anyway, that's what I'll do. This will be dy dx over x plus y plus 3 cubed. And what are the limits of integration?
Zero to infinity and 0 to infinity.
0 to infinity and 0 to infinity. If I wanted the entire plane, it would be minus infinity to infinity in both. Now, I'm not going to. Well, yes. Let's do take it at least one more step. So, what do I get for the y interval? And again, if you'd rather write it this way, be my guest. Do I need to make a substitution? Do I need to do a UD thing? No, because I've got my trick. So, what do I get when I integrate this -3 power?
-2.
-2 power, yeah. And I have to divide by -2. And what else do I have to divide by?
X plus
1. Because the coefficient of y is 1. So
I
that's
didn't know you could do that.
Oh, yes. That's what I call the A plus BU trick. A plus BU to any power. BU. So and when we do this, the B is 1, and the U is y. What's the A? Nope. I have to account for all of this stuff.
oh, it's x plus 3.
It's x plus 3. The A is x plus 3. And when you integrate a power of a linear, you get a power of the same linear. Then when we throw in 0 and infinity, well then, it's just going to drop that down to that. And this looks like bad news, except wait a minute, that's a negative power up there. So it's just gonna be 0. So, you know, you might want to do it this way in order to work out the antiderivative, but you don't want to forget that what you really have is this great big huge thing in the denominator. Okay, so that's what's going 0. And I'm just going to say etc. at this point. So the infinity gives you 0. And then I have a minus 1/2 times x plus 3 squared. What now? And that'll be positive. Anyway, will this converge or diverge, do you think? And if you know me, you're going to say it's probably going to converge, because I don't really like to waste a lot of time on things that diverge. It does converge. How come does it converge?
It's essentially 1 over x squared.
It's essentially 1 over x squared. And so if and remember the p-series test? Okay, this thing converges when p is greater than 1. Well, so here, p is greater than 1. If I had had a square here, if this had been exponent 2 to start with, this would have diverged. Because after one integration, you'd have, if this was a 2, you'd then have a 1, and then you integrate the 1 power on the denominator and get a logarithm. Well, that, we don't want to talk about it. But that's because it's the entire first quadrant. If I had a situation where there was like a little cusp or something at the origin, or anywhere else for that matter, then this might still converge. But I'm not going to go into that any further. All right. So we got some improper intervals there. Intervals in which polar coordinates might be helpful. Okay? And I very much recommend that you do problem 6. Use polar coordinates to find the formula for the volume of the sphere. What I'm going to do is to go back to the cone. I'm going to redo the cone. Or did you ever come up with something like that?
Oh, well, I mean, keep going, I'll pass them, don't worry.
All right, okay. So I might be here till 9 o'clock, is what you're saying. All right. Okay, so the cone. And I'm going to put it in this position that gave the incredible difficulty in rectangular coordinates. This is the one where it took me 9 pages to work the thing out when I did a dy dx integral on this. Anyway, I'm just going to write down what the equation was again. So it was x squared plus y squared over a squared equals z squared over h squared. And that's with this thing at the origin. And so then I changed this to a z minus h. And then we have h squared times x squared plus y squared over a squared. That was z minus h squared. So then we got z minus h equals plus or minus h over a times the square root here. And when I move the h across, oh, this is the way we had to choose the minus. Well, anyway, so that's sort of a quick review of what we've done before. So the volume is going to be the integral from, well, it's going to be a double integral over the disk. The base is a disk here. And I'm going to have that function, h minus h over a square root, so that's squared plus minus.
Why did you pick a minus?
Here's h. If I did h plus, it would go that way, but I need h minus. Okay, so x equals y. And what's the point of me doing this example again?
Because it's nasty.
No, that might seem that way, but no, I'm not that sadistic or masochistic for that matter. Actually, I am that masochistic because I did actually go through the 9 pages twice. I don't remember how many pages it was the second time. But the point of doing this again,
Because we have.
no, because now we have a new tool to work with.
Is it our cosine theta?
What?
Is it our cosine theta?
Yeah, there we go. Intervals in which polar coordinates might be helpful. And here is one. If I do a y substitution here, it would be a tangent substitution. It would give me a secant cubed integral. It would be awful. But
Would you sub that square root?
I can sub the square root as what?
R.
R. So polar, I'll have r squared equals x squared plus y squared. So that thing is just r. And let's see. And what goes out here? It's automatic.
RDO.
RD. Well, now let's see. That base, that's just a circle. And in polar coordinates, that circle centered at the origin would just go the,
R?
well, I was actually on the theta part here.
Oh, yeah, 2 pi.
And now I take a typical theta coordinate between 0 and 2 pi. And it goes from, the r goes from
0 to A.
A, okay. Because this is my circle of radius A.
I was just about to ask them. It's really good.
There we go. All right. Well, there is no theta in this because we have circular symmetry. And so I can factor out,
Yeah,
I can
everything's
take,
constant, right?
and the limits are constant. A is a constant, yes. And so anyway, here, I'll just do, H can be